Let's spend some time looking at the boot sequence that's followed by FreeBSD, as it differs from standard System 5 derived Nixes such as Linux and other Unices. So let's authenticate as our user Unix CBT. This will give us a GNOME desktop momentarily, within which we can launch a gedit session to take some notes. So currently our shell, as we've mentioned, is still the C shell, and let's go ahead and launch an instance here of gedit as a foreground process. And we'll concatenate the notes with due time that we've already taken thus far. So far, we'd like to discuss the boot/init sequence. This is important as FreeBSD differs from other distros that have a System 5 heritage with respect to the number of run levels that are available and the like. So this sequence is similar on x86 computers to a point. So the boot sequence begins with the BIOS whenever you boot your machine, whether physical or virtual. So whether running VMware or some other hypervisor, there is a BIOS that will handle basic hardware checks, initialization, and then searches for the first bootable disk, and in particular the master boot record on that first disk. So the BIOS makes a call to the master boot record on bootable disk. And this is determined by you, the administrator, via the BIOS. So you indicate, of course, which disk is to be made bootable. And of course, during the installation of the operating system, we spell out which disk slice is to be set active. That is the slice that will contain the MBR, the master boot record, and the remainder of the bootloader. So BIOS calls the master boot record on a bootable disk, and the master boot record contains the code which is within 512 bytes, so within 512 bytes, as is the limitation for x86-based systems. Now this information is for x86 compatible systems, so for x86 compatible systems, as other systems have fewer and other limitations. So within 512 bytes. Now once we get to this stage, there are a number of stages that follow to continue the boot process. So they are as follows. The master boot record, which is represented by a file called boot0, then calls boot1, which then calls boot2, which then calls the loader, or the bootloader. And then the loader finally sets up the system and calls init. So it seems rather convoluted, it seems like a number of steps, but if we enumerate it another way, step one is the system starts with the BIOS as you turn it on, which makes some basic checks regarding the CPU, the memory, and the storage devices that are attached, both optical, if applicable, and physical for booting, which is usually required unless you're booting across the network using Pixie, for example. After the BIOS, as is typical on x86 systems, the MBR is consulted. MBR on bootable disk. The MBR is limited, as we've mentioned, to 512 bytes. This is an old limitation that still carries over today for backwards compatibility purposes. That file is actually boot0. So this is a file located beneath boot0, and it actually resides outside of the file system, but a copy of it is maintained within /boot. So that we can reference it, and also so that if in the event that our boot sector becomes corrupted, we can use BSD label and fdisk to reinstate the boot sector. So the boot sector is limited to 512 bytes. That's where the master boot record is stored. So instead of 3 stages, which the FreeBSD documentation references, it's more like 5 stages. However, that includes the BIOS and the master boot record. Now this happens all quickly, of course, so it flies right by. You start your computer, if it's a virtual instance, you see a quick presentation. The MBR is consulted unbeknownst to you and to me. And then after that, as we've mentioned, boot1 is called. Now, what's so important about boot1? Boot1 is really a reference to /boot/boot1. It also resides outside of the file system. Boot1 contains just enough code so that it can load boot 2. So really what's happening with x86 based systems is that the bootstrap is segmented into multiple files for the sake of backwards compatibility. So this really loads boot 2. And this boot 2 code has enough information where it's able to locate the FreeBSD slice. And that's the FreeBSD active or bootable slice. This calls boot 2. And boot 2 has some more code and is able to do a little bit more, perhaps a lot more, than boot 1 with respect to booting your system. Boot 2 is a file located also in /boot, and it's simply labeled boot 2. Boot 2 loads UFS and optionally version 2, so UFS 1, UFS 2 support, or any other file system supported by BSD that you're using on your storage devices. In all likelihood, you'll be using UFS 2, as it is a 64-bit base file system which supports all of the storage available today. So it loads UFS, and this provides the support necessary to load the root file system. And then it calls /boot loader. The bootloader is the menu that we see when we boot our system. So that is the next step, the loader. Loader is located also in boot, as most, if not all, things are, with the exception of init. And it's simply a file named loader. Loader has the arduous task of loading the BSD kernel. So this loads the kernel. It has a simple interpreter which allows us to influence the startup environment, and it configures the initial environment. Again, it's a bit much information, especially if you're not familiar with FreeBSD. However, we'll try to spell out the files and walk through the process momentarily. Now, just as a note, when we say loads the kernel too is located beneath /boot, as is the case with Linux. So the kernel is located in, this is the default kernel unless you're using a non-standard kernel, that's /boot/kernel/kernel. This is the default FreeBSD kernel, and by default we mean by virtue of installing the operating system. So before we get too much deeper, let's take a look from the perspective of the shell at these various items. We'll open a separate shell, Control-Shift-T. So let's navigate into /boot. So as we've mentioned, when you turn on your system, the master boot record is consulted from the first disk, and that is in a file named boot0. So let's take a look at the boot files that are here. So here's boot0. Notice it's 512 bytes. And also, just in the event that you're concerned whether or not boot0, SIO, and boot1 are all identical, let's just relist using ls with the li option, which exposes the inodes of the file so that you can see that the files are indeed different. Same size as these three, but different. So boot0 is the MBR. In fact, there is a file named MBR, which is the master boot record file. So boot0 serves as our MBR, and it's a pointer, serves as an MBR. Boot0, as we've mentioned, has just enough code to be backwards compatible insofar as the x86 platform is concerned. Boot0 calls boot1, which is also 512 bytes, which has enough code to locate the FreeBSD slice that contains boot2. Boot2, notice, is 7680 bytes, and this contains the drivers necessary to load your file system root, which is usually UFS. From there, the handoff from boot2 is to the loader file. The loader file, as you can see, is 237,000 bytes, 568 bytes. This presents us with a menu, an interpreter, configures a default environment, and it calls the kernel. Now we're currently in boot. Let's navigate into kernel. And this is where we'll find the actual kernel file. So let's calculate its size, and that's 12,612,000 1,347 bytes, so roughly 12.5 megabytes is the kernel file that was compiled for this particular build of FreeBSD. So that is your basic bootstrap BIOS, master boot record, which calls boot 0, boot 0 calls boot 1, boot 1 calls boot 2, and boot 2 calls the loader file. The loader file gives us a simple menu. It'll accept a splash screen that fits within VGA specs, and it'll also give us an interpreter which will allow us to influence variables that affect the startup environment, such as passing parameters to the kernel, changing parameters, booting into single user mode. And then, after we've made a choice, it loads the kernel with various options, configures the devices, and then sends the handoff to init. Now, init is located in SBIN. This is the first process that runs on all Unix systems. And this process, as we can see, is 747440. Init within FreeBSD differs then from System 5-based systems in a number of run levels that are supported. So our next step, so it's really actually 6 steps, maybe even more, because init then sets up the environment. So init, which is located in SBIN, is the first process executed on all Unix and Unix-like systems. There is a system scheduler which is usually indexed at ID 0, for example, process ID 0 you'll find on Linux systems, but for all intents and purposes, init is the parent process for all processes. Now init takes over at this stage, and it wears a PID of 1, and it can be found by using PS. So for example, when we PS, let's use AUX grep init, you'll see that it is run by the user root. It has a process ID of 1, and this is the reference to init. Now, let's just note something about init. In BSD, init supports the following run levels, unlike sys V or System 5 systems, i.e. Linux. And they include 0, 1, 6, C, and Q. Let's just try to put this out. So 0, when executed, shuts the system. So this is a shutdown or a halt of the system. 1 enters single user mode for administrators. Run level 6, and these all are shared by System 5 systems. So if you're familiar with Linux, it's the same thing. 6 reboots the system. C blocks or prevents subsequent logins in the event that you're troubleshooting. So this is good for administrative purposes, or perhaps if you intend to relegate the system to a single user mode and need to ensure that no new users are connected to the system. And Q rescans etc TTYs for new information. etc TTYs is a very important file because it sets up the teletype terminals that are available to us, and that's read by init. So again, the BIOS, the master boot record, boot 1, or master boot record is boot 0, boot 1, boot 2. The loader gives us a menu. Init is called. Init then sets up either in single user mode, or if we tell it to shut or halt, or reboot, or to block, or to rescan TTYs, or just to come up in the standard run level, which runs services. So that then implies that init must call something. It must call a series of files in order to carry out its tasks, and that's certainly the case. Init then calls a series of files, including etc defaults rc.conf and etc rc.conf, And it does so via the RC process. So called via RC process or script. RC really means resource configuration. So resource configuration process, or RC. So init sets up the environment based on RC's help. Now what does that mean? Resource configuration means set up the environment, networking, services, and the like. Let's take a quick look at the traces on the file system. It also reads etc tty's as well, so we should also include that. It also reads etc tty's to know which tty's to make available where. So let's navigate to etc and let's take a look at rc.conf, the one that's in the etc directory. So this is the file that we should change in the event that we'd like to override directives that are defined in etc defaults. In fact, it's even spelled out here. So for example, when our system is up or comes up, there's some defaults that are understood for this particular system. For example, in order to leave the current network, it needs a default router. This is the default gateway. The host has a name, an FQDN, and the first Ethernet interface is assigned an IPv4 address and a netmask. IP version 6 is enabled. During installation, we instructed sysinstall to enable NTP date with a particular host, which should currently be up. We also instructed sysinstall to enable SSH so that we can connect across the wire. And we also made some changes to support this GNOME desktop environment that we're currently using. So init knows to set up these various items. So it performs some network configuration as well as network time protocol, the instantiation of SSH, and the setup of automatic detection for keyboard and mice for the GNOME desktop and X11 environments. But there's a larger file that's beneath defaults, which contains a number of directives. And let's take a look at this rc.conf that are pulled in by init. Now, if you scroll through this file, many directives influence how the system behaves with respect to all sorts of aspects, from ACPI to tempfs, to whether or not the PF firewall is enabled, whether or not the ZFS file system is available. And any of the directives that you see here can be overridden in the etc rc.conf file. So these are the directives that are common. So for example, the fact that the firewall is turned off is set to no could be overridden in the other file. It suggests that we make changes to the etc rc.conf file to override directives. But this is where all of the directives that govern how the system starts up will be determined. Another thing we should mention is that init also reads the contents of etc rc.d, and that's your resource configuration directory. In Unix, a .d directory basically means that there are a number of entries that are to be processed from that directory. This particular directory references networking and services. So houses networking and services scripts. And you'll find an RC directory, rc.d directory on all Unix systems, including Linux. So let's take a look at rc.d, and if we ls, you'll see a number of items. For example, the DHCP client or devfs to automatically detect and create device nodes for us. NFS client, NFS server. Somewhere in here should be SSH as well, within the S section, SSHD. Now let's take a look, sending the output to less. You'll notice that there are a number of items that are uppercase. Daemon, file systems, login, networking, and servers. These items are initiated before anything else, because the other processes tend to depend upon one or more of these uppercase items. So let's just note D1 uppercase items in etcrc.d are called prior to lowercase items to provide requisite support. For example, if you take a look at the networking file, the references here are very important for any service that requires networking, which is practically most services, such as SSH, for example. So these items are run first. And the RC documentation spells out the exact order. Here's a reference to inetd, for example, the super server which calls any number of services such as FTP. So that's basically what init does. Now, we didn't look at the TTYs file. Let's take a brief look at that file. This is the file that instantiates the terminals that are available, including the one that houses the GNOME Display Manager, which accepts the graphical login and provides us with this graphical environment. So here are the virtual terminals that are defined. TTYs V1 through V8, or V0 that is through V8, which are 9 TTYs, but they're accessible via F1 through F9. On F9 you'll find GDM. It references XDM, but it calls GDM because we have it installed. And then we see references in the event that there are serial ports defined. Notice the Getty processes that are referenced. You'll find this across NIX-based distributions. Getty is a process that sets up a line and calls upon invocation or access the login process to authenticate users and provide them with a shell environment. So let's just note etc TTYs provides get TTY lines which initiate per user instances of login to authenticate users, and if successful, provide them with a shell, which of course is what we get when we log in at one of the consoles. When we're logged into the GNOME desktop environment, however, pseudo terminals are made available. And if you notice, there's a section called pseudo terminals below. And here are some references for pseudo terminals, but they're dynamically allocated via the GNOME desktop environment. What are those pseudo terminals? Dev PTS. The PTS is short for pseudo terminal. TTY, regardless of the shell that you're logged into, will always reveal the pseudo terminal to which you're connected. So the fact that this is pseudo terminal 1 means that there is pseudo terminal 0 allocated somewhere else, and that's this particular shell. And a W will show us that gedit is running on pseudo terminal 0, which is this window that we currently have blocked. So that is your startup environment. Now what we should do at this stage is reboot the box and just take a look at some of those items to see how they play out. Again, it's very similar to Linux, but the big difference is with the way init handles run levels. It handles run levels, but it doesn't provide as many configurable run levels, such as RC n.d, for example, 2 through 5, as you find on standard Linux and System 5 based systems. Let's save this particular file. It's going to be, in this case, UCBT BSD8x notes.txt. We'll have to concatenate them. So let's just call this one UCBT1 so that we know it's from this particular host and that we can concatenate them accordingly. And this is complaining that we're low on space. We can always grow the file system later on. So that's out of the way. So again, quickly, BIOS, MBR, which is, of course, boot 0, boot 1, boot 2, loader, init. And then after init, you get login, whether it's graphical or text. So this is basically how systems boot, regardless of operating system, so long as x86 is the underlying platform. Now, with that said, how do we reboot the system? A number of ways exist. First of all, you need to either be a member of the operator group or be root. In this shell, we're not root. We can SU, and it doesn't allow us to because this user is not allowed to SU into the system. Another way would be to log off and then do so as another user, or try to shut down from this window, and it should prompt us if we try to restart. And in this case, no prompt, it took the restart. but it wouldn't allow us to SU. That's a separate file that controls that configuration. Now here we are at the boot menu itself. This is the master boot record being called. Let's press F1. Now we go through boots 1, 2, and loader. This is the loader. It happened so quickly, but because of legacy reasons, this implementation is still required. So again, to recap, we rebooted the system. At the point where you saw the VMware logo, that's the BIOS. At the point where you saw the option to select an environment to boot, we had already completed boot 0, and we're well on our way to boot 1. We selected an option which led us to boot 2 and quickly into the loader, which read the loader conf from /boot. It's all quick. So what are the options? We haven't perused the options. We've only defaulted to option number 1. If, for example, ACPI is not operable or misbehaving on your system, you can disable ACPI. It's not as often, it's rare nowadays. Most systems support ACPI, most OSs support ACPI, and they work harmoniously. But in the event that there's a problem, that is an option. Safe mode also, too, will get you out of a jam in the event that you're not able to boot in some cases. But the really important options include number 4, which is the ability to boot into single user mode. As an administrator/engineer, this is the important mode because it allows you to troubleshoot, for example, disk problems in an exclusive mode known as single user mode. All NIX-based systems support this mode. So option 4 presents us with single user mode. It's a hook, it's a shortcut. It's so important, it has its own menu item. So 4 takes us to single user mode. Let's take a quick look at that mode and we'll just examine the boot environment and then reboot to this menu and then continue with the boot process. So again, what you're looking at here is the bootloader. This is the free BSD bootloader. Had we used, let's say, a Linux bootloader like Grub, the menu would look different. There would probably be a pretty splash screen, which is supported by the free BSD bootloader. Now let's navigate to 4, and this will boot into single user mode. The white text that's bolded on the screen indicates that the kernel is probing the hardware for various devices to provision for our usage once the system's up and running. When the text alternates from white to a shaded color, perhaps you could call it gray as it is there now, we're now within the realm or the auspices of the init process. Now, in the default configuration, FreeBSD trusts that your console is secure. By that it means only authorized people should have access to the console, whether physical or virtual. So in a data center, it could be both physical and virtual. So the idea is if you are entering the cage, you have some sort of authorization to do so, and you're trusted, you shouldn't be prompted. That can be all changed in the security section. We'll ensure that we secure the console so that a password is required in the event that a rogue person accesses the virtual or physical interface. So by simply pressing enter, we're given a shell without being prompted for a password. This is a C shell, a limited shell. If you echo, for example, shell, returns nothing. However, the root file system is mounted. DF, for example, confirms that. So there is the root file system with the H or human readable format. We see that the first SCSI disk, which is, as we've mentioned, or SATA, DA0, the first slice, S1, and the first partition, A, partitions run A through H. As we've mentioned, B is reserved for swap slices. C represents the full slice, and D or C represents the full partition space on the slice, and D through H will allow you to provision additional partitions within that slice. This is the root file system. Notice we don't have the other file systems available that we've provisioned during installation, such as /temp, /var, /home. However, we have the basic file system, which includes the boot code. So let's take a look. We'll navigate into boot. Now we've mentioned that when the system comes up, it loads a number of files. Let's look at boot star, loader, kernel, and these are the files that are loaded. So again, system starts boot 0, boot 1, boot 2, loader, calls the kernel loads various modules. The loader also reads the loader conf, which calls in various loader files to help set up the environment. And then the kernel is called from the appropriate directory. Now just a quick note, let's take a look at boot start, for example, that we should point out. And that is that if you take a look at boots 0, 1, they're both the same size, but more specifically, look at 1 and 2. They total the size of the boot file. This tells us that boots 1 and 2, which are integral because, of course, when you boot the system, the BIOS finds boot 0 immediately as being in the MBR. So boot 1 and 2 are really split from boot. So the boot file represents boot 1 and 2. So as a quick note, boot is really equal to the concatenation of boot, let's just place it this way, both boot 1 and 2. So this is one way to look at it. But it's split out for legacy purposes to fit. And that's how our system comes up. Now we are in single user mode. We don't have a run level process like with Linux to tell us that we're in single user mode, but we know that we're in single user mode. Why? Well, 1, other users cannot connect. 2, there are no networking services. So that tells us we're in single user mode. Even on System 5 systems, whenever you see that you have no networking, so for example, a netstat, can't even find it. Let's try ifconfig. These are all tools that are normally up in multi-user environment. Notice that for ifconfig that nothing's configured, so we're not able to accept or generate traffic. So that tells us we're in single user mode. And that's what's important about this mode. That means we can now do things such as mounting file systems to debug problems, for example, or simply backing up in exclusive mode content without running the risk of the content changing. So that's why this mode is particularly important. Now, how do we know what to mount if we had to troubleshoot something? If you navigate to etc, there's a file called fstab. This is the file system table file. This spells out the various file systems that are available. And at any time, you can mount any one of these file systems and work on them. So here are the mount points that we've defined during installation. So they're always made available. They're just simply not mounted in single user mode. So single user mode, let's just note, single user mode mounts root exclusively. Important to note. And this is the case usually across Linux and Unix-based systems. Now, if you've finished your work in single user mode, there are a number of ways in which you can reboot or start your system in multi-user mode. Control D is one way, or exit. So you can either issue a Control D, and that performs a fast boot, bringing up the system in multi-user mode momentarily. And of course, here comes the GUI. So it's a fast boot because FSCK checks on the hard disk are ignored. This brings up our mode very, very quickly. Now, let's go ahead and try to log in. And this will bring us back into multi-user mode. And to shut the system, there are a number of options that are available, so long as you have access. But we don't because we're not root, and we're not able to SU at the current time. Now, if you'd like to access a console where you are root, you could use, for example, Alt F1 through F8. So let's pick, for example, arbitrarily Alt F5. And now we're at our Alt F5, which is TTY v4. At this console, let's log in as root. And now we can perform tasks on the system. Now, when your system comes up, just two things we should mention. There's so many things we could mention, but two things that come to mind. If you'd like to see the kernel boot environment, you can run kenv. This dumps the environment that was supplied and created by the kernel. So let's clear screen and dump it, piping the output to less. Less is a one-page display program which allows us to paginate output. So Here are the variables that were passed into the kernel environment. For example, the fact that the boot file is called kernel, or the fact that it booted in single user mode. Any of these variables that you see here can be specified at the boot 0 menu or the loader menu that you see by dropping into the command interpreter and using the set command. So you could set boot underscore single equals yes if you'd like to boot into single user mode. It's a longer way of doing it since you have a menu option you could select. But nonetheless, the idea is any variable that you see here can be explicitly mentioned during the boot process in the event that you're troubleshooting or you need to tweak or influence something. So these are the variables that are passed in. The hints that you see concern devices that are on the system. And there we see the kernel still kernel. No kernel options were passed in. The full kernel name includes its path relative to boot, relative to the root of a file system, which includes boot, boot kernel, kernel, and that it loaded from disk 1S, the first slice on, or disk 1, the first slice on the first partition, and that the loader loaded the following config files. Device hints to know how to set up devices, IRQs, addresses, loader conf, etc. And we see some other settings here. It's able to detect that it's an Intel-based system, Phoenix BIOS, the BIOS version, the modules path. So it loads from boot kernel, boot modules, any modules that are needed to support your system. So kenv tells you how the system came up, the environment that was loaded to bring your system up. Another important command that you should consider running is dmessage. This is available on Linux as well. Dmessage dumps the recent instantiation of your system and the devices that were detected as a consequence. So let's dmessage pipe to less and examine one page full at a time. So you can see the various devices that were detected. It detected, for example, parallel port, VGA, ACPI, USB. In fact, it found 2 USB buses, USB 0 at 12 megabits per second, version 1, USB 1, 480 megabits per second, and more importantly, of course, it found, well, in fact, it shows the number of ports that it found: self-powered 2 ports, self-powered 6 ports, self-powered. This is actually correct. The hubs that it found on the wire, on the USB bus. DA0 is more important because this tells us, it knows it's a virtual or VMware disk, but it's found it, and it knows the transfer rate, 320 megabytes per second. And it also knows the size, the number of sectors, which we had to cut up to, or segment to create our partitions on our main slice. So DA0 is the main disk, and DA1 was also found, which is a similar configuration. And you're normally looking for your disks. It also knows the CPUs and the memory. So for example, it knows this system has 512 with an available 477 after items were loaded. So dmessage gives you a sense, look at the copyrights all the way back to the 70s, gives you a sense of the hardware that was detected on the bus. It detected 2 CPUs because we've provided from our quad core processors, we provided 2. And it sees those, CPU 0 and 1, as well as other items. So dmessage tells you what was found on the bus when the system last came up. You can always consult that on both FreeBSD and NIX-based systems to see if there are any issues detecting items. Now, to shut your system, a number of ways exist. You can execute halt, for example. That turns off your system. You can also execute shutdown, but shutdown will accept options such as this will shut it now, which is equivalent to init 0, or you can reboot now, which is equivalent to init 6. Since we like init, we reference it to reboot simply as init 6. It's less to type. So init 6 will reboot quickly, and we'll take another look at the boot menu, the loader. So let's bring this back up, and you'll quickly see items fly by. Shutdown script is called. That's rc shutdown, rc.shutdown in etc. And here we have our boot option. Let's F1 to continue. And this will quickly set up the various stages, bringing us to the loader menu. This is the loader menu. Spacebar to pause the countdown timer. So we've looked at single user mode. We've used Control D to enter multi-user mode. Option 5 provides us with more verbose logging in the event that we're troubleshooting, let's say, kernel device detection. Now let's take a look at 6, which escapes to the loader prompt. Now we have a prompt. It doesn't look like much, but question mark shows you the possible options. Grub within Linux supports this as well. So some shortcuts include reboot, if you need to reboot the system, or to set variables, for example. So you can reboot, set, you can unset, or you can boot a particular kernel if you know the path. Let's say you have other compiled kernels, or one or more. Let's show what variables are set. Now notice that this list resembles what we saw when we executed canv, because again, it's an amalgamation of the loader.conf and the other called files like device hints that are brought in and loaded at runtime. So notice no references to boot single. It shows the kernel that's to be loaded and so on. So these are the variables that are called when it boots. You could influence things. For example, you could set boot_single, which we saw, equals 1, which is Boolean for on, and then type boot, and this will boot into single user mode. Again, the bright white means that the kernel is performing its probe, and when it shifts to that gray off-white color, it means init has taken over, and we're basically in user mode. We see the DVDR was detected, and now we can get a shell. So now we're in single user mode, at which point we can simply reboot instead of entering multi-user mode. So let's reboot again. And F1 to continue. Loader will come up shortly. And we're back to the loader menu. So again, we have this loader prompt, which allows us to set variables if necessary. It even allows us to load modules if we'd like. So if there's special hardware that FreeBSD isn't picking up, you could load it on the fly, let's say from a floppy or from somewhere on the disk. So this is basically your FreeBSD bootloader menu. You can use BSD label and fdisk, and it's in the documentation, to relabel your bootable slice in the event that there's a problem bringing your system up. So let's go ahead with our normal boot using option 1. And this will boot. The white means, again, probing for devices. And this will boot into multi-user mode. And then because gdm_enable is spelled out /etc rc.conf, the GDM process will come up in place of XDM and prompt us to log in. FSCK is always checked unless you're booting from single user mode to multi-user mode. And now our system's back up. So again, we've covered the standard boot environment for x86 systems running FreeBSD. This information applies to other BSDs as well, such as NetBSD, OpenBSD, but since FreeBSD is the major one, we're covering it.